Welcome to mathandstuff.com. Today we do arc functions. And the easiest way to get to the material is to go from the home page down to the videos page. On the videos page, under the title, High School and College and School, you'll find 8.3 arc functions. That's where we're going. And you'll see a selection on the right. We're going to the web page, and that's where we'll be working, but there is supplemental material. You can just download it here, or you can download it from the web page. So let's begin. We go to the web page. As usual, before I even go through a lesson, what I do is review material that you need. So let's see if I can actually find it. Okay. In the beginning of the semester, we looked at the functions that you would be learning about in Precalc. And we've already done the basic ones: identity, opposite, reciprocal, squaring, square root, and the more exotic, greatest integer. Then we got into polynomials and rationals. Then we did the exponentials and logs. Now we've already just completed graphing the sine, cosine, and tangent, and also their reciprocals. Today we work on the arc functions. The arc functions are the functions that undo the trig functions. So let's continue. Course outline says this is for inverse trig functions, day 20 of the semester. So you only got about 8 more days lessons to go. That's where we are. This is what we've done. A review. The word inverse means undo, and we do have a sketch pad for looking at the inverse. We've used this before. I'm using it again just to remind you. First, you have to see if you really have a function. You have a function if it passes the vertical line test. In other words, for every x, there's exactly one y, no more, no less. Then you have to see if it passes the horizontal line test. That means for every y, there's only one x. And if both of those things happen, one may take an inverse. And you get to play games with this a little bit, because the square root is a function that you can take an inverse of, but if you do try and take the inverse, and then reflect it over the line y is equal to x, and then you go to draw the inverse, you see that it looks a lot like a parabola, and it should, but it's a parabola that part of it is chopped off. And let's see if we can find restricting the domain. Here's another square root function. I'm just going to show you that if I don't restrict the domain, then I have an issue. Let's make it -1. This is no longer a function that is the inverse of the blue one, because it's got too much stuff. So you have to restrict the domain. And that's what we're going to be doing today. We're going to be restricting the domain to get the arc sign. All right. Let's go back to inverse. You now have the idea of inverse. And we did take an inverse analytically, and we have to remember to switch the domain and the range. When you switch the x's with the y's, the old domain becomes the new range, and the old range becomes the new domain. We also looked at trig function angles in both degrees and radians. We looked at similar triangles and similar figures. We looked at the trig functions of the 30, the 60, the 90, the 45. We were using what I called Oscar had a heap of apples. There were other ways to approach defining trig functions, but I chose that one. Your book, I think, uses this one first. But you get to the same place. For each of these angles, you can compute using Oscar or SOHCAHTOA the trig functions of those angles, and that gives you I gave you some practice here. You should have done this, connect the dots. We then looked at the reciprocal functions and the co-functions. Co-functions, you think complement. We're not going to worry about that today. We've just looked at the reciprocal functions. We've looked at the idea that though we used a circle to look at the angles, if you took that circle and stretched it out on a plane, that would work also. If you go around the circle counterclockwise once, you get 2 pi radians. If you go around the circle twice, you get 4 pi radians. Around again, 6. Around again, 8 pi. If you go backwards, if you go in a clockwise direction, around once gives you negative 2 pi, then negative 4 pi, and so on. All that can be graphed on a coordinate plane, and we used those graphs. We looked at them going around the circle. We looked at them in each quadrant. We looked at the quadrantals. We analyzed the unit circle as shown in this picture, and then we got to the graph paper. I'm going to make this a little bigger. And I asked you to print the 3 planes per page paper because we were going to use this to graph what we already knew would be the functions, page up, as we went around the circle. So you could look at the unit circle this way, you get the same answers. We're now going to do a graph of it. We have not graphed it yet, but once we did get to the graph, we noticed that the sine wiggles a lot, looks just like the cosine. The sine is an odd function, the cosine is an even function. We did all that, and we also looked at the reciprocal functions for the sine and the cosine. We didn't take the reciprocal of the tangent. That's as far as we got. So this is where we're headed today. And look at arc functions in detail. An arc function is an inverse function, a function that undoes the work of another function, and we looked at inverse geometry sketchpad. That's when we looked at this. We were looking at a square root function and how we reflected it. Then I went to this page and you saw about the restricting. Now we look at the arc sine function. In blue, I have a sine curve. I know you know that. But now I've introduced the reflection, or a reflection of the blue sine curve across the line y is equal to x. So the x values and y values switch. And I'm just going to move this and so you can see that they do indeed switch. Now, the green function is not nearly as long looking as the blue one. The blue is the entire sine function. I would love to be able to undo the entire the sine function, but I can't do that unless I restrict the domain. So that's what we have to address first. Restricting the domain. We have to restrict the domain so that if you have a number x and take its sign, you get a number y called the sine of x, that you knew. And if I try and scroll it, let's see if I can get it to pi over 4. Now, let's try and move it a little more. There we go. Here's pi over 4. If I go to pi over 4, that's 45 degrees. The sine of 45 degrees, square root of 2 over 2. And that's a positive number. I need to be able to undo positive y values. I need to be able to undo 0 y values, and I need to be able to undo negative y values. So I have to have the ability to get answers for each of those things. That's why I drew this little picture over here. And let's look at the picture on the web page because it's bigger. The goal is to be able to undo a sine in order to find the angle whose sine you took. A function which undoes the work of another. Strictly speaking, the symbol s to the negative 1 is arcsine. Arcsine is the angle whose sine is. That's what we need to know. The angle whose sine is. If we try and find the arcsine of 1/2, that means the angle whose sine is 1/2. Let's look at the toy. Here's a half. I'm going to try and go to the angle whose sine is 1/2. Here's a half. Here's the sine curve. The angle whose sine is 1/2 is pi over 6 or 30 degrees. That's a positive number. But we know from looking at the trig functions of all the angles, that the sine is positive in the first, and the sine is positive in the second, and it's negative in the third, and it's negative in the fourth. We have to be able to get each of those numbers back. We have to be able to undo the 1/2 or the negative 1/2 to get us to the 30 degrees or pi over 6. So again, this is what we do. We have to restrict the domain. I've drawn a picture of the sine curve dashed, and here you see in pink the sine curve, and these answers on this side of the origin are positive, and the answers on this side of the origin are negative. So if I just restrict the domain of what I'm going to call the arc function to numbers that, and we have to have all of them, have to be between 1 and -1, then I can look at just this piece of a curve. Just the blue is the reflection of the pink. The green here is the reflection of the blue. Okay, so here we go. We're back to restricting the domain. If I declare this is how we're going to do it, then it'll work. The arc sine of a positive number should be an answer in the first quadrant. The arc sine of 0 should be 0 because the angle whose sine is 0 is 0. If the arc sine, the number you're taking the arc sine of, if it's negative, you wish it to be down here. Now, nobody calls it the negative first quadrant except me, that I know of anyway. And I call it that because when I swing the angle in a negative direction, if I had swung it in the positive direction, then this is the first quadrant, this is the second quadrant, this is the third quadrant, this is the fourth quadrant. That's going in a counterclockwise direction. If I swing it in a clockwise direction, even though I'm in the fourth quadrant, I'm swinging it negative, so I'm declaring this to be the negative first, the negative second, the negative third, the negative fourth. No one that I know other than me does that. But I've communicated that if you wish to find the angle whose sine happens to be a positive, you better get a first quadrant answer. If you wish to find the angle whose sine is 0, you better get 0. And if you wish to find the angle whose sine is a negative, you better get a negative first quadrant. Now, let's look at the calculator and see if the calculator does that. If you want to find the sine of 30 degrees, you better get a half. That'll tell you your calculators in the degree mode. So, if you want to take the arc sine, the angle whose sine is a half, you better get 30 degrees if you're in degree mode. And that arcsine function is sitting up there just above the sine, and the arc cosine is above the cosine, and the arc tangent is above the tangent, just as the square root is above its inverse, the square. The 10 to the x is above its inverse log base 10, and e to the x is above its inverse natural log. So let's turn on the calculator. And just, this is the way you check to see what mode you're in. It's the easiest way to do it. Sine of 30 better give us a half. Yep, we're in degree mode. We're not in radian mode. So I'm going to put in, I want an arc sine. And I want the arc sine of negative 1/2. And I get a negative 30. Negative 30 will mean that I'm going this way. I've gone I've gone clockwise, and therefore have a negative angle. Let's go back to the web page. I think you now understand this picture. Now I want to go to the tangent picture. The reason I'm going to the tangent is because the sine is odd, an odd function. The tangent is an odd function. So if I want the angle whose tangent is a positive, I want to get a first quadrant answer. If I want the tangent of an angle, if I want the angle whose tangent is 0, I want to get 0. And if I want the angle whose tangent is a negative, again, I want it to be what I call in the negative first quadrant. Let's see what it looks like on the calculator. Let's put in I'm reminding you that the tangent of 45 is 1, and that the tangent of 315, which is a 45 in the fourth quadrant, I get a negative. So if I want the arc tan of a negative 1, I better get a 315, but my calculator will not state it that way. It will correctly give me a negative angle. So big, big, big deal. Yeah, you got to know that. Now we go to the cosine. Cosine's in even. Cosine's in even. Let's look at a better picture. If I need the angle whose cosine is 0, the angle whose cosine is 0, that's pi over 2. Well, it also happens at negative pi over 2. So which one should we use? How should we play the game? How should we restrict the domain? Well, let's look at something else. If we want an angle whose cosine is positive, that happens in the first quadrant, and an angle whose cosine is negative, that happens in the second quadrant. So here we go from 1 down to 0, down to negative 1. We pass through positive values, we pass through 0, we pass through negative values. So what I want to do, I want to look at the arc cosine. It's an even function. An even function doesn't look like an odd one. Find the picture. Okay, here's an odd. And in order to get some negatives, some zero, some positive, I use this piece of the curve. In order to get some negatives, some zero, some positive, I'm going to use this piece of the curve. Let's just look at it in the sketchpad. Here's a cosine. The blue function is a cosine. And I need to have the ability to find the angle whose cosine is positive, the angle whose cosine is 0, and the angle whose cosine is negative. And that's why, let's see if I can pull it, drag it. That's why I get this curve. Here's the mirror image of the blue curve. I think you understand. The arc functions in graphic form. I think you understand the answers you get on the calculator. Another way of saying exactly what I said up here, if you put in an x value that's positive, you want to get a first quadrant answer. If you put in an x value that's negative, you want to get a negative first quadrant or fourth quadrant, but measured negatively. If you want the angle whose cosine is 0, it's pi over 2. If you want the angle whose cosine is positive, it's in the first quadrant, and the angle whose cosine is negative is in the second quadrant. Tangent works the same as the first. It's all written there in case you want to read it again. Okay, so baby expressions are just do one function. If it's written as arcsine, or if it's written as arcsine like this, use the capital arc sign, meaning the principal. Just as when you had a square root. Let's just put that in the notes. When you simplify, you take the principal root. When you solve, you take all roots. When you simplify, you take the principal root. You're really doing what's called the arc sine function. And that's where if x is a positive, you get a first quadrant angle. If x is 0, you get 0. And if x is negative, you get a negative first quadrant is what I call, or fourth quadrant measured clockwise. That's how you simplify. You get one answer. When you solve, you look for all answers. In order to solve this, you have to undo the sign. You undo the sign with an arc sign, just as you undo a log with an exponentiation, and you undo a square root with squaring, and undo squaring with a square root. You take the inverse function. Here you get an x. And this is just simplifying a nested expression. Now we go with the angle whose sine is 1/2. Well, you can think of 30 degrees, but write pi over 6, because that's 30 degrees. And you want all of them. Oh, let's just write it this way. You want it in the first quadrant, and you want it in the second quadrant. This is pi over 6. This is 5 pi over 6. But you want them all. So what I want to show you is that you knew that this would be in the first and that would be in the second. Those were places where the angle whose sine is 1/2 could be found, and that happens within the first quadrant and the second quadrant. But there are other places where, here's 1/2, other places where, no, move it. There are other places where the sine is 1/2. Here's one of them. Here it's in the first quadrant. Here it's in the second quadrant. Here it's in the first quadrant after 2 pi. And here it's in the second quadrant after 2 pi. This answer happens every 2 pi, and the other answer happens every 2 pi. So I go plus or minus 2 pi n where n is and now I have all the answers. So it depends on what I wish to do as to what kind of symbol I get. If I'm just simplifying an expression, I'll only get one answer. Here, I'm simplifying a negative. I better get a negative answer. Here, I need the arc sine of the sine. I just get x. And if I want the sine of the arc sine, I just get x. They're inverse functions. Again, arc sine of the sine of x, I get x. Sine of the arc sine of x, I get x. They're just inverse functions. Arc sine of the sine of 30, better give me the 30. Arc sine of the sine of 210, 210 is in the third quadrant. In the third quadrant, the sign is negative. The arc sine of a negative better give me a negative angle, a negative first quadrant or fourth quadrant measured counterclockwise. Here's the summary of what I said about solving. If you're going to solve and you only want answers in one revolution, they should happen in two places, in the first quadrant and the second. If you want answers all over the place, all possible answers, then you want to go every 2 pi and get all the answers. However, if you try and find the angle whose sine is 3/2, let's see what the calculator does. Let's find the angle whose sine is 3/2. Better give me a problem, because if you look at what the sine curve looks, if you look at the sine curve doesn't ever go up past 1. And I think I can try and show you that. It won't do it. Won't go past 1. So the answer to this question is no solution. Now, that's everything you need to know as far as mathematics goes. Here's everything you need to know about doing work that you have to produce for a test. In the gray box, these are the ways you can solve a triangle. When you were a kid, you just knew how to do the Pythagorean theorem. That's all you could do. When you got to geometry and learned about a 35, 60, 90 and a 45, 45, 90 right triangle, you could do more work. You could then find some of the angles sometimes. Now you're looking at conditions where you are now, given that you're with a right triangle, you're going to be able to do even more than you could before. Before, you could solve a right triangle. 45, 45, 90, and 30, 60, 90 were easy. Now, because you now have trig, you can do more with what looks like less. But there's still more to go. There's still more you won't be able to do. So let's look at some problems you can do. The problems that you usually will see have to do with a right triangle and what's called an angle of elevation or an angle of depression, or just other stuff like a ladder leaning up against a building. There's the ladder. Here's the building. A pole casting a shadow. Here's the pole. There's the shadow. You might want the length of the shadow. A tree of unknown height, but with a known angle of elevation. Here's the tree. Here's the angle of elevation, and there's the distance away from the tree. So I've set up so that we'll do two problems now. They're ready in the notes. So I'm going to read this because it's more visible here. The world's steepest road is CA 108, California 108, along the Sonora Pass in California. its grade is a rise run of 13 to 50. Stated as a percent, that's 26%. What incline, what angle of elevation is this? So we'd go to the notes and we open up World's Steepest Road. Has a rise of 13 to 50. It rises 13 for 50 on the run, and that's 26%. What angle of elevation is this? We need a trig function that relates the angle, the side opposite and the side adjacent. That's the tangent. We want to get at the angle, so we want to undo the tangent. Let's use the calculator since we don't have another way of doing it. We want the arctan of 13 over 50. We get 14.57 degrees. I'm going to lay it out so that I can find all the pieces. Triangle C is 90 degrees. That means I can draw a right triangle. A is 2.5. C is 6. I want to find the other angle measures. I could go for the Pythagorean theorem and find what B is. I don't have to do it this way, but I'm going to do it this way. A. B. C. .54. 5.45. Well, now I have to get an angle. Doesn't matter which one I choose. I know that this is 5.45. I know this is 2.5. And I know this is this. And if I go for angle A, I could use the tangent. I could use the sine. I could use the cosine. We've done tangent enough, so let's try a sine. Arcsine. 2.5 divided by 6. 24.62. And B should be easy. $90 minus the answer I got last time. $65. I think you're okay with that. So we've done 2 problems. Your homework is to do the connect the dots. This requires the arc functions. The rest of your homework is to write and solve a word problem similar to question 1, using a situation usually stated, meaning make up it using these words as listed above. Homework is due. Let's make it midnight Friday night. Take care. Enjoy. I hope this was not a waste of time. I'll see you next week.